So let me also thank everyone to come here at this, by the way, really sunny morning in Brussels, and morning early quite, yes? So let's bet ourselves how good guys are we. So we woke up, yes, and made our dedication to learn something new and to develop open source together to crowd and continue our job here. So today I'm going to present two features, one for myself, it's a new authentication plugin PARSEC, and another one which works together very well is Zero-Config SSL. So first, I've been already talking about PARSEC, you know, in the past event. So I decided to start from the perspective of network and how do authentication plugins work on their own, and let's see how the Handshake is built on the protocol side. So first of all, a setup, we have a client, we have a server, and let's consider that the TCP and SSL is already done for now. We will return to SSL later on this RDS part. And first, who starts dialog is a server, and it already tries, well, first it sends a 20-byte nonce, which is a random string. It can be used later or maybe not. And it will try to decide with the client which authentication plugin will be used. So the server always has some authentication plugin considered default. And this is the string that the client receives first. There are a couple of plugins that can be default. On the other hand, the client can accept this plugin, or maybe it has another consideration given by a user, so it responds with its own authentication plugin and the username. Of course, the server may reply like, oh, I don't know this authentication plugin that you're sending to me. Or maybe, oh, this user cannot use this authentication plugin, so it may suggest another one. And this may continue for a couple of round trips. Reasons. What are the reasons? And why do we have different authentication plugins, different authentication approaches? First, of course, it's a password-based authentication, right? That's what is typically used. But also, it can be Linux PAM, PAM, or GSS API. For a reason, for example, if some specifically protected role, like administrator is used. So I can imagine the setup where the admin role doesn't have a password authentication, and it also can be done through PAM or GSS API, or maybe Windows domain network usernames. I guess we don't have such a plugin, but anyway, it's also a possibility. And this is why, and the client can have just a default setup. First, try to use a password. If a password is not available for such protected roles, then try to use another plugin, which can be what I mentioned, the password-based something. Okay, and then after the plugin is finally chosen, it sends its first message, so the plugin starts working. If it's PIM or something like that, the message is typically just empty, and the authentication ends, well, soon enough. I'm not sure how soon, but I guess it needs at least one more round trip. Am I correct? Does Linux PIM need another round trip, or is it just okay from the server?
There are two options, you can go either way.
There are two options. So, and for password-based plugins start from some message to client. The concept is that we don't want to send the password from the client to the server. We don't want to shine it on the network. We don't want any mere watcher, just read your password. Yes, we have TLS, but not always. It can be disabled, and we don't want to make this consideration. So this approach is zero knowledge. We show no information about the password. So this approach is called yeah.
And one addition also, we also want to be sure that the server doesn't get the password in clear text at any point in time.
I couldn't hear you.
We also want to ensure that the server doesn't get the password in clear text at any point in time, because if the user is reusing the password.
Absolutely correct, yes. So this is why we try another approach to authenticate. It's called a challenge-based. So the server-side plugin sends some string, usually called challenge, and the client tries to generate a string based on password and this challenge. For example, it can just calculate a hash out of concatenation of this challenge in the password and send it through the network. That's not, well, is it secure? I'll just tell a little bit later. But in this way we don't send the password through the network. This is not what typically happens on HTTP or web authentication. I guess password is just sent, and we used to live with that during the HTTP era. Can you imagine? But anyway, in a good case, there is just a single round trip. This is an optimistic case where the default plugin matches the plugin that is provided by client. And this means that the client cannot authenticate with the plugin. The user supplied the password, and the authentication happens in the single round trip. And everything like challenge response, username, they are batched into a single TCP packet. But not every plugin can do this. As I said before, the server sends these nonce, and this is used as a challenge for a default plugin. Not every plugin, not every password-based plugin can use these nonce as a challenge. Only 2 plugins can do this. For this moment, it's native password and no password. And I want to just tell a few things about these 2 plugins. They are quite old plugins, and native password uses SHA-1 to store on the server side SHA-1 of the password. Yes, at least it's not really a password, but common SHA-1. And our plugin even uses some home-brewed hash function, which is not even SHA-1. So problem with that is, for example, storing on the server just SHA-1 of the password. If the table of these hashes is stolen, then the attacker can use this hash to make a successful authentication. And also, if it can, well, it's SHA-1, so it's a very popular hash. So it's a good chance that there is a quite saturated rainbow table is available somewhere on the web. So this gets the attacker a good chance to reverse a hash to a real password that has been used by user, and well, compromise it as a result. The good thing is that these 2 plugins, both native and old, they use both server nonce and client nonce to generate the challenge response. So native password on the client side also generates its own nonce. So there are 2 nonces, 1 client and 1 server. They are concatenated with a hash of a password, and then another hash is taken, and this is what is sent by the network. A good approach, well, at least it protects from man in the middle quite well. And finally, after that, the server can send OK if the hash matches the expectation of the server. And then what we like is finally SQL begins, sent by the client. So as I mentioned, there is a problem with using SHA-1, and the next generation plugin with a quite pronounceable name ED25519 tries to fix this approach by using an asymmetric cryptography. So instead of storing SHA-1 on the side of server, it stores first it uses password as a private key for this signature function, and the public key is stored on the server side. What happens there? First, this plugin sends its own nonce, and it's 32-byte long. And in comparison to the nonce that the server is typically sending, it's also generated by SSL. So extra protection and a bigger size. And then, on the client side, let's sign this nonce with a password used as a private key. So, and this signature is what is sent to the server. Then the server receives the signature, it can try to validate. The validation happens with the public key. Public key is derived from the password. And this public key is what's stored on the server. As a result, well, if the table with these public keys is exposed, well, at least the private key, which is a password, will not be compromised. That's the idea of asymmetric cryptography, right? On the one hand, right. But on the other hand, well, still generating a rainbow table out of public keys and mapping it to private keys, that is our password, is kind of possible. Well, maybe it doesn't exist for now, but it's feasible and it can be done in some foreseeable future. So it's not considered very safe to just save the public key as it is. That's one thing. Another thing is that this plugin didn't use client-side nodes. So what can happen is one possible attack is met in the middle. Let's suppose that we have some active node in between client and server, and this node can pretend for client that it's server and for a server that it's client. It connects, client connects to the server, but actually this this node receives this connection first, if it's acting like a proxy. Yes, and it sends the response instead of the server. And for example, it can just send its own nonce with some freak value like 0, and as a result, it will have a 0 nonce signed by our password. Yes, the signature is 64 bytes long, so it may be kind of safe. But yet, it's another information, extra information about the password. So this can be problematic. And also, no client nodes, and this man-in-the-middle problem may even reveal the SQL sent by the client, because the server is not validated here. Actually, the only thing that is validating is zero configuration SSL, and I'll talk about this just in 5 minutes, I think. So finally, the last generation that I'm presenting is our new plugin, PARSEC. It tries to fix all the problems, and it tries to save the value that is stored on the server side. So even if the table is exposed somehow to the attacker, it will be super hard, basically infeasible to reverse it to a real password, and even to just private key. So instead of using the password in a signature, it still uses the ed25519, but instead of using just password as a private key, let's use this string, PBKDF2 function of the password and the salt. So it's salted. And it also uses both client nonce and server nonce, as it was in the previous generation commits. And here's what's stored. A public key derived from this PBKDF2 function, and also the salt, and some extra data about the algorithm that is used. So more data is set. It's also 32 bytes nonce, and the algorithm that is used, and the number of iterations used by PBKDF2 function, and the salt itself. So the client will have all the data to generate this PBKDF2 from the password, and finally send the challenge response, which is a concatenation of two nonces signed by this hash.
One question.
Yes.
The salt, is it user-based or server-based?
The salt is server-based.
So the server has one salt for all users. Same salt for all users.
No, it's per user. The salt is per user. Usually, if it's not per user and server-wide, it's called pepper.
But that means that the attacker man in the middle can get the salt for that user.
Yes, it can take the salt, and that's no problem. The important thing is that this salt is per user, so it's impossible to build the rainbow table. If it would be a single value global for at least one server, and well, consider, for example, some very important server with a lot of users, then an attacker can think about building a rainbow table just for this single case, this single
What is the salt? 1 byte, 2 bytes, 64 bytes?
That's a good question. I'm just coming to this. So all the features of PARSEC are listed here. We try to use the library provided by the system to sign and to validate the signature. We support OpenSSL, GNU-TLS pretty well, and also they are used for PBKDF2, and now it's used with the SHA-512 with the 1024 iterations. Unfortunately, on Windows, well, the Windows encrypt decrypt, they cannot make a public key derivation from the private key, which is normally supported by this signature algorithm, but Windows can't do it. This is why we supply a portable implementation which does just this part, and the rest is done, to my belief, with also Windows provided internals. So all the salt sizes and etc. Conform the current NIST recommendations. And by the way, the NIST recommendation is to use this much iterations and some modern enough hash function, which should be less than SHA-256, and actually I'm using 512. 32 byte scramble, 32 byte nonce, and 64 byte signature. So all this is quite big to protect us for a foreseeable future. And now we have a little intermission where you can ask questions or follow the references, where you can find some additional articles, documentation about PARSEC and about zero-configuration SSL. And also Sergey's article about the zero-configuration SSL. Yeah, please.
Iterations, when do you pay that cost for creating the user or for each connector?
Okay, first, it's done on the server side when the user is created, and then PBKDF2 is generated each time by the client. But the server cannot even do that because it doesn't have this data. It already has only a public key derived from the PBKDF2.
But so do we need to do those 1,000 iterations for every connect?
Yes, for every connect on
So
the client
what's the
side.
cost per connect? It is big compared to. So what's the cost for using PARSEC in performance compared to whatever?
For server, it's zero cost because it's done on the client. And on the client, yes, there is some cost. We didn't measure it, but we consider that the security is more important.
We still need to know it. I
Good
don't
thought.
know. Sergey, do you know?
No, we didn't have that. But this is the whole point. The point is to make Connect slightly more expensive, so that when you try to brute force, you need to repeat it
Yeah, but
millions
it
of
is
times, and then it
slightly-
won't be done repeatedly.
Slightly, this means that we have to wait until the sun goes down before we connect.
If you try to brute force, you'll need to wait until the sun goes down.
Yeah, but even in normal connect, because it's
You said that the number of iterations suggested by NIST is 1,054. That's actually from 2000. Now it should be something like 60.
From 2000?
Yes, now it should be something like 600,000.
Well, I've checked in the NIST recommendations. As far as I remember, it removed the exact number, but it suggests to make it as high as possible, and the previous versions had something about 1,000.
That's from year 2000. Now it should be at least 200,000, 600,000 recommended.
Oh, we are out of date.
Anyway, most of the drivers they use connection encoding nowadays. I don't see any more like people connecting this coding.
Which year is that version that you?
2000. Also,
2000? Yeah.
When the standard was
No, check the newer version. I bet there is a different value. I mean, no exact value.
recommended for PBKDF2, HMAC SHA-256 is 600,000.
SHA-256, but what about SHA-512?
200,000.
Ah, so it's 256 is 200,000, and for 512 it's.
So 600,000 for 256 and 200,000 for 512.
That's something outdated.
I can give you the.
Well, I just have a summary in a ticket about the suggestions from NIST. So let's move further. And now, as I've covered most of the MariaDB handshake part, let's recall the grand structure of our handshake. First, we have TCP and SSL, yes, then MariaDB, then some OK and something else. What something else we will see just soon enough, and then SQL. Now let's focus on the TCP and SSL part, or actually TLS. So TCP is not important for us here, but what happens in TLS? The purpose of TLS, or SSL as the older and outdated version of TLS, is to make a secure key exchange, so that both client and server will share a common key, however, not exposed to any watcher, any mere watcher. And what it can use is, well, it can do different things. It may have may supply different data. For example, first TLS should decide also which key exchange algorithm to use. It depends on different configurations, parameters of the server and the client. Namely, it can be a TLS version, etc. actually. And also it can have extra round trips and all stuff. But for us, what's important is a key exchange part. Usually it's de-facto one, and it can be some other key exchange algorithm. TLS supports few. So first, after TCP three-way handshake ended, server responds with its own private key, public key part of the element or something else. And the client also shares his part of data. Then they combine and get a secure private key that is not visible for just a sniffer. But it can be exposed with a man-in-the-middle attack. In this case, also, as it's supposed by man-in-the-middle, it pretends for a client it's server and for server it's a client and just makes two separate connections. One with the client, one with the server. And makes two key exchanges with them. This way it kind of makes a secure channel with both and works as a proxy. So, as a result, the connection happened, and yet we have man in the middle that may access data from both sides. The typical solution for that is to have some trusted third party, or as it's called typically certificate authority, or CA. And that's how modern web works since HTTPS and now with the QUIC. So what it does is just connects to a third party and validates the keys provided by one of the sides. Usually it's server, but also TLS supports validating a client as an extra. And usually it's pretended to be typically as the only way to make a secure connection and to avoid man in the middle. But it's not. Another way is to have a pre-shared secret. Just the problem is typically in HTTP and all web, we don't have any pre-shared secret. But here we have. What it is what the value that is stored for an authentication plugin. It's a password hash, or if the plugin is good, it's a sorted password hash, or in case of PARSEC, it's even PBKDF2 derived and sorted public key. So this is a common pre-shared secret that is known for both sides. On the OK stage, server now can calculate this hash, taken out of this password hash, nonce, and the common certificate fingerprint obtained by the TLS part. And on the client side, we also know all these three values. So server sends this hash, and client side calculate just the same hash from the values it has and compares it. That's it. If the values match, then we have a secure connection, and the middle is not present. My favorite slide. I mean, Sergey's favorite slide. Indeed, zero configuration SSL is zero configuration. No extra parameters are needed. Just one thing that connector J, connector Node.js, they have SSL disabled by default. All you need to do is enable it, and on connector C, it's already enabled by default. So even there, no extra needed to be done. And who wants again to follow up the references, please? And I have a
previous slide. You actually have to have the reason MariaDB.
Thank you for this note. Exactly, yes. Zero configuration SSL is available from 11.4 and PARSEC is from 11.7. But also already released, so yes, feel free. And we recommend to use it. What time? Yes. We recommend to use it. It's hard to configure a third-party trusted authority. So this is just an easier way to establish a secure connection for you. Well, thank you for this morning talk.